Okay, we will get started momentarily. Now, couple of standard housekeeping announcements. Essentially, if it is okay with you, Dr. Bagchi, we might want to keep the session in two stages. If they have, is that okay, or how do you plan?
Two stages meaning
In the sense,
it's
I mean, if they have questions, do they need to wait until the end or in between or something,
no,
without disturbing the your train of thought?
yeah, I feel like you could, ask the question right away if it is relevant to what I am showing. If something doesn't make sense, because I don't, I may not be in the same wavelength as you. There might be things that I think is obvious, but you might not, or vice versa. um, and so some interruption of that is greatly, I would appreciate, because you're telling me what I need to go
Okay.
deeper into or explain. But there are some natural breaks or pauses. Perhaps we can stop in those places and have a more
Okay.
of a discussion.
All right, then without further ado, let me express my pleasure and privilege to welcome Dr. Sugato Bagchi from IBM USA. I mean, to me, he's a friend. I know him for God knows how many years, 34, more than 30 years, I guess. And he has been working in IBM for 25 odd years, uh, recipient of the 2, 3 outstanding research award. And knowing him, he is not particularly fond of elaborate introduction, so I'm going to cut it short. I first came in touch with him actually in a train from Kolkata to ISC Bangalore. I'm in Bangalore while joining there. So we that was in 1986. We go back that long. We shared the same room in the hostel and a variety of other stuff. And he, among many things, I mean, he has a master's from ISC Bangalore and a PhD from Vanderbilt University in robotics related AI, intelligence, control system, intelligence machines, those kind of areas. So that's a brief. But to me, something I think he has this rare combination of a sharp mind and a good heart. So with that, I welcome Dr. Sugato Bagchi to me, Sugato, to today's session, please.
Okay, thank you, Professor Samajdar. Maybe the first time I'm calling you by that name, but in front of all your students, I really appreciate the invitation. Thank you. Thank you to the rest of you for, sacrificing some of your evening to listen to all this stuff. And um, so, yeah, I have been, working in this area for a long time. I remember taking my first course in artificial intelligence at IISc, and I had no idea what it meant, and I did very poorly because all they did was teach us a programming language, and I was like, what does learning a programming language have to do with artificial intelligence? And I was quite depressed about that. Um, in fact, I think that course I got my lowest grade. I will not tell you what it was, but and but then I got into robotics, and again a lot of it turned out to be more math than artificial intelligence, but there was a lot of math. And then, I started understanding and appreciating neural networks when I started doing during my PhD. Uh, and I have been motivated by it since then. Neural networks went through some kind of a decline in like the 90s and the 2000s. And then only, I would say, since 2011 has it started making a resurgence, and now it is where it is. And so I'll try to take you, what Professor Samajdar wanted me to do was to give you a introduction to what this is all about, including, I hope it's okay, some math, but it's not that I will ask you to do the math, but I would ask you to appreciate the math. And, it is all nothing more complicated than additions and multiplications, except in one particular area, but that is also very simple. So from your backgrounds, you have legal backgrounds. A lot of you have actually practiced, and it's very useful because a lot of this is not just technology, but how you apply the technology in an actual real world situation. So let me just start with that. So here is a problem. So maybe Professor Samajdar has to deal with this, or maybe,
Uh, Sugato,
yeah.
maybe you can show the full screen, okay,
Oh,
of the
am I not?
presentation. No, it is
Oh, yeah, 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 yeah. Sorry. Thank you for reminding me.
sure.
Yes.
It's all right. And just check align your microphone a little bit so that your voice is a little bit louder.
Okay. Let me make sure. Okay. Um, so this is where we want to start. So you are basically, I hope you can hear me.
Yes,
Is
yes.
it okay? So you are, you have to make these decisions. You're a college admissions officer, and one of your jobs is to make sure you admit students that are expected to finish college, not get admitted to college. Um, so, you want to kind of look at but at the point of admitting the student, he or she has, finished, let's say high school, let's say this is undergraduate. Um, so you have in this following kinds of information, their high school, grades or marks or, GPA or whatever it is that you get from taking all those tests during your school years. You have that information. You also have like maybe some entrance exam or some standardized test you had to take one day, and maybe on that day you had illness or something happened, but or you did unexpectedly well for some reason. But it's all one day, but it's good because it's standardized. Everyone has that exact test score. You may also have a lot of demographics information, the person's background, whether their parents went to college, their, income, you know, anything that, gender, age, even, religion, anything else. You have all this information. You may, most of the time you can be biased by that information. You may look at somebody and say, oh, no, this, maybe, usually the people of that background, they don't really succeed, and so you may say, I don't want to look at that at all. I don't want to look at uh, 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 that at all. I just want to be motivated just by the numbers and make sure I am fair. But you have all that information. And then how do you learn how to do this? So to do that, what you have is a whole bunch of students that did finish, did graduate from your college from the past. You knew their entrance exam, scores. You knew their demographics. You knew their high school, scores. And you knew whether or not they passed. They completed their, let's say it's a 4-year degree or whatever. They got their degree. You know that. So you can now say, okay, I have this experience from the past. How do I use it to build a machine? So can I reduce the work I do? Maybe I don't have to go through all these applications. Can I make an AI do this work for me? So this is the first question. Then if you say, yes, I want to look at that, then the question is, what kind of AI? What is AI and what kind of AI will help solve this problem? Then, you might want to understand, how does this work? How will it work? What does it do? Can we see what's going on inside that AI? What is it actually doing? How is it making that decision? Can we look at that? Um, not just its output, but its insights. How do we know when it when it's successful, when it fails? Why does it fail? When will it fail? Then beyond failure is fairness. Can it be fair? It may not fail. It might very well predict every person who is expected to graduate and say these people will graduate. But is it being fair? Is it being fair to everyone else? Um, and question is, who is it being fair to? As a college admissions officer, it might be fair to you because you say, look how great a job I do. Now, from now on, everyone I admit, they all graduate. But is it fair to the students, perhaps, who did not get? So that's basically an issue. Let's say we will revisit that. But now you say we introduced this word, artificial intelligence, this phrase. And now we have jumped from that course I took in 1987, maybe, to today. And
Sugato, I'm just sorry to interrupt. Maybe a little adjustment of your microphone position, please. Okay.
okay, okay,
It is.
uh, okay. Let me try it like this. Okay, yeah. Is it good?
Yeah, I think it is better. Is it
Okay.
better, Akash, Mr. Bhuiya?
Yes, yes.
Yes, this is better now.
Okay, okay. Thank you. Thank you.
Okay. So now when you hear of artificial intelligence, you hear of OpenAI, GPT-4. Every large company, a tech company now has their own artificial intelligence. What are called large language models that can chat with you. Google has something called Bard. There are other startups that are doing very well. Um, Microsoft's search engine Bing has now been powered by AI with GPT. So there is a lot of hype and actually a lot of amazing things that are happening in the area of artificial intelligence now. The question is, how did we get here? First of all, what would we consider to be artificial intelligence, and what are these things that are underlying these various headlines that you see? Okay, so within the area of artificial intelligence, so now I'm going to dive into what exactly is powering these technologies. So, but I would say, there is artificial intelligence, but then within artificial intelligence, there is something called machine learning, where a machine, learns how to learn. Machine learning is not the only kind of artificial intelligence. There are other, more logic-based reasoning, planning. If you have to go on a vacation and you need to then say, okay, to do that, I first need to find a good place. I need to then buy airplane tickets. I need to buy hotel. You need to do a sequence of, you need to plan out a sequence of actions, knowing that also at any time you may have to replan. You may have to change your plans, and that's a sign of intelligence. Unlike the other way that you just show up somewhere and we usually call them, okay, why didn't you plan ahead? And it is a sign of intelligence that you can plan ahead. There are also things like causal systems. Before getting into machine learning, I'm trying to say that is not it. This is only the start. Causal systems can look at data to understand what causes what. What is the sequence of actions that go from one to another. Might be very useful when you're reasoning or when you're planning or when you're problem solving of some kind. And humans do that a lot. We know that if there is a leak in your roof, it might be caused by the rain, but it's not that the leak causes the rain, it's the rain that causes the leak. So, we know it. It's obvious to us. For a system, they just see two things happening at the same time. It's raining, my roof is leaking. It has to figure out which came first and which caused the other. Or is there a third thing that is causing both of them? So there's a lot of reasoning, etc., that has to be done. And then there's theorem proving and other signs of intelligence. But we will stay in machine learning for today. Within machine learning, there is what is called supervised training. Here, you are learning by being taught, by being trained. You're given examples, you're given various information about these examples, and then you are kind of told, how to, what to predict from that one example, and then you're given thousands of such examples, and you're kind of being supervised, sort of like what you do in a class when you are given exercise to do, and then you're given the right answer at the end, and then you can say, okay, this one I went wrong, this one I did right, what did I learn from it, how do I adjust my internal model of how to solve these problems. There are, of course, other ways. There is unsupervised um, pattern discovery. You say, I don't know, I'm not going to give you any supervision. I'm just going to throw a lot of data at you. You figure out if you can find some correlations between them. You see if you can find some clusters of data, groups of data. That, I don't know what those groups might be beforehand. Tell me, and maybe it'll be useful to me. So that's unsupervised. Other things like reinforcement learning, for example, when you're playing chess, you may know whether you did well or not only after you lost at the end. And then you say, okay, that move I made in the 13 moves ago, I should have done that versus this, right? So you can have a way of kind of giving blame or credit to moves of the past in the past. And how do you do that when all you have is any moves in the future, you have some knowledge of whether you won or lost, or lived or died. So that's supervised training. We will stay in supervised training. All of these things we will show you, everything we'll show you is based on supervision. Then under supervised, there's artificial neural network is one of the ways in which you do supervised training. Beyond artificial neural networks, though, there are many other ways of supervised training. Some of them, unfortunately, are kind of now being not, focused on as much, but they all have interesting things to offer, I would say. But we will stay in, and I won't go into the details of these things, but they are very interesting in their own right. But we will stay within the realm of artificial neural network. Now, within artificial neural network, let me just go through these a little bit more quickly. There's deep learning. You may have heard of that phrase. We'll try to understand what deep means in deep learning. Within deep learning, when you apply it to language, it creates models of language. We will try to understand what that means. Within language models, then there is generative language models. It's language model not just to understand what you're saying, but actually to generate language. And this is what has impressed people recently. And then within generative language models, there is what are called instruction tuned. It's not just generating anything but it's generating based on instruction. You give it a one sentence instruction. It understands that instruction. It may not ever have seen that instruction before in its life. In that sense, it has not been supervised for that instruction only. But it can understand that instruction given in English, given in the natural language that this has been trained in, typically English. And then given that, now you can train these, you can tune, I would say, these large language models. LLM here may mean very different from what you might think of. And that is, in fact, one of the challenges of language. There is a lot of ambiguity. What is in this context, what does LLM mean versus in another context? Here, LLM just means large language models. And for some reason, they try to focus on the large, and we will see why. And then it is these instruction-tuned LLMs that, in fact, are then what are behind all these headlines and all these various technologies now that we can use. Okay, so if you look at all this, artificial intelligence is just an objective. It doesn't tell you how to do anything. It doesn't even tell you what to do. It just says, we want to create some, quote, intelligence that is artificial. What does it mean? Okay, so that's just an objective. these machine learning or within it supervised training are problems. So now I can say, okay, to be intelligent, I need to be able to teach this machine how to learn. A learning system is an intelligent system. And within that, something that can take supervision, that can take training and learn from that training is a problem that I want to solve. And then everything else below it are just various ways, various implementations, techniques, solutions for the problem of supervised training, for solving the problem of supervised training. So as you can see, the core of it, the root of it is this. Um, that is, I would like, artificial neural networks is at the base of all of this learning. And so what I wanted to do in this presentation is to kind of explain in some level of detail what this is. And this understanding this needs a little bit of math. Please let me know if it makes sense or if you have any questions. But I'm sure all of you have the necessary skills to go through and understand, and more importantly, appreciate what's going on. Since you are not artificially intelligent, you did not need to be supervised that much. You have the natural intelligence. So to start with, before we go to artificial, any questions so far actually at this point? Then let me.
Yes, Jatin.
Yes,
Jatin
go
has a
ahead.
question.
Sir, is the
Go ahead.
objective of artificial intelligence, am I audible?
Yes, you are.
Okay. So, sir, is the objective of artificial intelligence is to achieve parity with human performance or rather to exceed it and accomplish tasks beyond the scope of human capability?
Uh,
So, what
well,
goes into the mind of like a creator?
yes. So the question is which human, the most intelligent human or the least intelligent human, and how do you measure intelligence in a human? Um, many things, it is way beyond human performance. There are in the area of natural language processing, which is what I work in. There, humans had created a lot of benchmarks where they had human various kinds of questions and tests, um, all about learning, understanding language. There, a lot of these tools have reached that level of human performance, but then humans can always say, wait, but that's not fair. We should ask a harder question. It has some of the technologies have achieved average levels of scores in medical licensing exams, for example. I don't know about law license. Um, the only example I know about law was when it was quickly observed that it was fake. So there is, some hope for you, but whether it'll reach the performance of good lawyers, hopefully not. Uh, but in other cases, it is much better. If you look at radiography, looking at X-rays, finding problems, looking at MRIs, I wouldn't say much better, but it doesn't have the problem of feeling sleepy or being distracted or looking at all the other ones it has to do in the next 1 hour and feeling depressed. It doesn't do all that, and it can find minute differences. And what it does is say, look, I will identify for you these areas that no, you wouldn't have been able to do. Now you make apply your judgment. So it's a good combination of doing things that it's better than a human, and then letting the human be the ultimate judge of things. And of course, there are other things like giving directions. You don't even think of it as AI, but now you can ask for, how to go from this place to that place, and it'll tell you and it'll give you turn by turn directions. Um, do you think of that as artificial intelligence? No. Does it do better job than a human telling you turn right here, turn around, turn now? Oh no, you missed it. Curse at you. It doesn't do all that. Um, so it's better in those sense, in some sense. self-driving cars. Sometimes it's obviously wrong, but it is better than the average human, especially, average human, late Saturday evening after coming out of a bar or someplace. So, it's, sorry for long answer. Yeah, go ahead. Yeah. Diptiman. Yeah, good question. Most of the time you hear of artificial neural networks now, but there are a lot of technology, there are a lot of systems that have been trained, have been, with things like random forests, a lot in, for example, in the medical domain, where there's a lot of data, and random forests are very good at finding, learning from that. So it is not the only thing. For language, for image, for all of these things where it is what we call unstructured data, like words of English or a picture or sound, there the neural networks do a lot better. Speech processing, recognizing speech. But in other areas where it's just numbers anyway, other techniques can also do quite well. But yeah, all of these pictures that you see here, all artificial neural network based. Okay, let's move on. But please keep the questions coming. I'll pause. Hopefully, I'll remember. But interrupt me, as I said, at any time if it is related to, what is this? Okay. Okay. So now, before we go, sorry, this is not the artificial, but the real neuron, of course, a picture of it. And not even a picture, a drawing of it, let's say, of a neuron, but helps to understand what a neuron is in your brain. So you can see it's basically a cell, that round thing here. Is my mouse visible? But anyway, this round thing in the middle here is the cell.
Yes, it's visible. It's
Okay,
visible.
yeah, sorry, I don't know if there is a better way. Then what you see are all these little branches, these are called dendrites. These bring in information. Um, then you see this long insulated, think of it as a cable. These green things are basically insulations. Insulated cable that comes out of the cell, connecting to another neuron. The blue thing here at the right-hand side is the dendrite of another neuron. And dendrites are these branches. And so you can basically think of this neuron taking input from all these dendrites. And you can see something funny, interesting going on at the tips of these dendrites that you can actually see at the end of this neuron, that it makes connections to other neurons, basically. And the connections can be strong, they can be weak, um, they can be a long distance away from the center of the cell, such that the signal will get, decrease in its strength as it gets towards the nucleus. So basically, this neuron is accumulating in its, center electrical signals from all of many other neurons with different levels of strength, right? Now, one of the inputs might be very strong, but like, for example, this input might have been very strong, but it has one little tiny little connection, and maybe you don't, get a lot of that strong signal to this cell. But ultimately, something happens here inside of the center, inside of the cell, is that all of these get added up and added up. And if it reaches a point, it can then activate. And something interesting happens here in this area, in the base of what is called the axon. And if all of these signals add up to something big enough, then it can shoot out a signal, and it can say, okay, I myself now have fired. I have received enough input. In spite of all the attenuations, in spite of all these weak connections, I've received a lot of input, and I think there's enough for me to shoot out a signal. And of course, this is, if you say this to a neuroscientist, he will or she will laugh at you. It's not exactly how it works, but good enough for our purpose. Um, and it shoots out a signal. Now this signal then gets sent out through what are called these synapses. These are the connections. It makes this neuron, the one we are looking at, makes with other neurons through these blue, in this picture, blue dendrites that are connected to another neuron, and on it goes, 100 billion times. And you multiply this one picture 100 billion times, and that is your brain. But basically, this is what happens inside of one neuron. So the same thing now. This is now we got rid of all the messy biology and chemistry and electrical engineering from this picture, and now we are purely in a mathematical space, but using those same symbols. You have some inputs shown here on the left-hand side. We like to call the inputs x's, x1, x2, x3, etc. These inputs now then can get weakened. It's not directly the input, like you said, like you saw there. The dendrites are of a variety of strengths. So we call those weights. So each of these inputs gets multiplied in our algebraic world with a weight. And then as a result of that, then gets summed. So we add up, just like in the real neuron. We take the x1, multiply it with w1. We take the x2, multiply it with w2, and on and on. X7, multiply it with w7. We add them up. We add all of those multiplications up. And then we get some amount of a number as a result of that summation. Okay, so now this is not good enough. So far, it's a very linear. You're just adding and multiplying things. And here is the only bit of nonlinearity we will introduce into the system. This is a function that will take that input and kind of, if it is very high, it will squish it to, let's say in this case, and we will use this example throughout, this particular, what is called activation function, I should have written it here, squishes the signal. If it's very high, it'll make it +1. If it is very negative, because x1, these are all numbers, it can be negative or positive. Weights can be negative or positive. Again, in our algebraic world, we have left the cellular domain behind us. So no negative numbers in biology. So now we have, but if in our case, we can have negative numbers, negative weights. And if the number is very negative, then we will squish it down to -1, because we don't want the system to kind of explode with increasing larger and larger and larger numbers. If it is any number in between, near 0, if 0, it'll be 0. And if it is near 0, it might be whatever it is. So it might be linear in some level to some level. And then it's kind of squishes the top and the bottom to be +1 or -1. Does that make sense? Okay, I'm assuming it does, or and we will see what happens with that. And then after it goes through that, now you're guaranteed, in this case, a number called y, and this number is guaranteed to be between +1 and -1, -1, right? Or maybe 0, maybe something in between, but more likely to be between, always guaranteed to be between +1 and -1. Which we like because it keeps our system kind of in control. It doesn't go haywire. And so this is basically, the output. Now, do you like this output? When we can calculate. So as I just went through, in painstakingly, hopefully, we can use this math to calculate a prediction of y, given all the x1, x2 up to x7 in this case, can be anything, any number. Now what we will do is we'll provide the actual y. So this is what, let's say initially, when the neural network is not trained, when this neuron is not trained, these weights will be all random things. We'll see examples of all of this, by the way. How much? Okay. But we will give it an actual prediction. And then when we do, we can train. So we can say, okay, you predicted a Y. There's a big difference between what you predicted and what the actual is. And if I take the difference between them, that is, in some sense, you can think of it as a loss. This is the loss this neuron is suffering right now, because it, if it was zero, then it has zero loss. That means it was exact, it was accurate. But if it was a big, if the difference is big, either in either direction, positive or negative, then we have a loss. And then this loss can be used proportionately to adjust all these weights. So say, okay, I have a big loss. I have a big, let's say, positive loss, then I must need to increase all of these weights. I have a big negative loss, I must decrease these weights. And in proportion to that loss, I will adjust these weights. There is, in the real actual usage, there is calculus involved, but we don't need to get into all that. But you can just think of that loss being influencing how those weights will change. And that's how you train from one example. And now you give it a million such examples, and hopefully it'll learn something useful. Does this make sense? Any questions about this? Don't be shy, please. Okay. So now I will simplify. Simplify so that I can visualize, because ultimately you learn a lot from these visualizations than you do from algebra. So here I will visualize, simplify. There are 7 x's, now only 2. Why only 2? X1 and X2, because now I can put this X1, X2 on my screen, which is only 2-dimensional. So now I have these 2 inputs, X1, X2. They go into 2 weights, W1, W2. There's always a W0, also called bias weight, for a reason that maybe the more mathematically minded of you can understand, or maybe I'll ask at the end why we need that bias. They get added, they go through that activation, that squishing function, to generate a y between +1, -1. Let's say with initial values of weights that we have for W0, W1, and W2, the blue area is when, the values of X1 and X2 for which it predicts +1. And the orange area is the values for which it predicts -1. And the fuzzy area in between is, where the 0 passes and numbers closer to 0 than to positive or -1. So that's in that area. And you can see it's kind of like a straight edge. So this we will get into why soon. Now we actually give it the real values for these
Sugato,
dots.
is there any way you can increase the size of your cursor? Maybe choose the laser pointer or something there. If you are using PowerPoint,
if I were using PowerPoint, is
the
there a
marker
laser? Where is that?
left bottom corner.
This one, laser pointer. I didn't even know such a thing existed. Amazing. Ah, you see a laser pointer. Great. You see me move it?
Yes.
All right. And what happens? Okay. Interesting. Okay. So these dots were the training examples. So when so far, I just went back one step. And here I didn't tell you how these dots should be predicted. What is the actual value that we want for these dots? Okay, we just have the predicted value, which is any dot you see in the blue zone, we will be predicting as, let's say, the blue class, and any dot in the orange zone, we will be predicting as the orange class. One thing I must mention right now is we are doing some kind of classification. I should have mentioned it earlier, but a lot of the supervised learning is about classifying things, whether, as we saw in that example, the classification might be, will this person graduate 4 years of college? And the answer is yes or no, because you either graduate or don't graduate. There's nothing in between, let's say, in this case. So blue might be graduate, and orange might be will not graduate. So all these dots we predict all these dots are, applicants, and, they have a X1 input and they have a X2 input. And then we use those two inputs to decide whether they will graduate or not. Okay. All right. Okay. So, but now we say, but guess what? Hey, how do I? Sorry. It's fun. So the laser goes away. So if I have the laser, I cannot do anything else with this. I cannot go forward. Or maybe, okay, let me go forward like this. Okay. Space bar still works and laser is still here. So I give you the actual Ys. These are the blue dots you see. So when you see a blue dot in a blue background, the machine got it right. When you see a blue dot in an orange background, those would have been students that would have graduated, but you didn't even admit them. Orange dots on a blue background means the machine predicted them to have that they will graduate, but they would not. And orange dots in an orange background, machine got it right, wouldn't have graduated, and that's what the machine said. So wrong. It is like you can see it got half of it wrong, because it's a random initial weight. We don't know what, we have not trained it yet. But now we will give it all these colors of the dots. And we, this is where we will train. So we will see real examples, by the way, pretty soon. So given the fact that the machine has all this loss, every time you see a colored dot against the background of the wrong color, that's a loss. And every time you see it against the right color, that's not a loss. And so we will feed all these. When you're doing right, when you're doing wrong, we'll give you all those weights. Sorry, we will give you all those losses as feedback. And then we expect the machine, using its math, to update those weights, W0, W1, and W2, only these three numbers in this case. And hopefully, if it works, it'll look something like that, where now it has adjusted the weights such that on the left-hand side, we can see that it has put most of the orange dots in an orange background. That means those students, it rightly predicted them to not have, they would not graduate. You still see some it let through because, they are mixed, you cannot really predict they're mixed with some of the blue. So, those machines are not, exact, not going to be accurate. Nothing can really predict the future, but it does much better. This is what it has learned. It has no biases of humans. It can do this all the time. And it can do this, as you can see, in quite well for this cartoonish picture, right? So this is what a machine, one neuron, and this is also being done by one neuron. When you have only one neuron, basically you can draw a straight line to differentiate between your classes. Again, classes in this case are two classes, one pass and the other fail, let's say. And we can basically draw, a line between that, and this is going to be a straight line. Why? Because this is just a linear combination of the inputs, the X1 and the X2, and the weights, W1, W2, and there's a bias, W0. And this is the line where it is 0. Everything above it is positive, and below it, or to its left, negative, but we then limit it to being -1, being the minimum, and +1 being the maximum. Any questions? All right, while you think, let me take a sip of my tea. It's morning here, still waking up.
Just a quick one. I mean, when does it stop? Who gives the criteria? Is it supervised or does it,
when does it stop learning?
No, yeah. I mean, here, this in one iteration, it is coming to that. So
okay, we'll get into that.
okay,
But
all right. Okay.
thing,
I don't want to put the horse before, the cart before the horse.
Yeah, but it never really stops. You can
Oh,
see,
it
get some
really
new data.
never stops. Okay.
When do we stop learning? Hopefully not anytime
Okay.
before. But yeah, it will stop when you have exhausted all the training data. But sometimes it likes to go over, not always, it likes to go over the same training data multiple times, right? Like you do when you are studying for exam, you go over the same material over and over and over again. Why? Because you want to learn that in new contexts. You want to learn the same information. You want to be exposed to the same information in new contexts. And so you may want to use learn over and over again. Now, how many times you're going to learn over and over again? For us, there's an exam, so unfortunately we have to stop learning. You cannot stay up all night, or maybe you do. Um, but, and then you have to stop learning because you take the exam. Here, there's no exam, so it can keep learning if you give it more and more data. But that's a good question, because the other question is, what should it look at? Should it look at all the old information? Should it, in this case, should it go back 10 years? Should it only look at the recent examples? There are many things, to consider, and sometimes, unfortunately, it's not considered. Anyway, let me move on here, but please feel free to ask questions, because now we're getting into the demo mode. So now we will take this picture from the past and try to make it come real. So the way I do it is there's this website created by Google called tensorflow.org, playground.tensorflow.org. You can go there, you can play with it at your own leisure. What I have is a version of this that I where is it? Here. So I use this. You can see my my screen, right? It's a white screen now instead of a black.
Yes, it is visible.
No more laser pointer, unfortunately, here, unless there
No,
is.
but your pointer is visible.
Because it's white. Okay, sorry. So here, hopefully this looks the same as what you saw here.
Yes.
Sorry, here. This is the same, except for all this picture to the left is gone, but you see this same thing here in a much nicer, cleaner laboratory environment, not as messy. Let's make it a little bit messy. So there are blue dots and orange dots. Our job, the machine's job, is to predict which dot is blue, which dot is orange. It cannot see the dots, the color of the dots. It only has two inputs. The x1, it's a number. It's not any number. It can be a number. It can be fractions. It can be anything. It can be high or low. It doesn't matter. And x2, another number. So basically it takes two numbers. And again, as I said, the reason we like two numbers is because we can put it, x2 is along the vertical axis here. x1 is along maybe the horizontal axis. And so we can kind of see all these dots. So as soon as you see any dot, you know exactly what its x1 and its x2 values are. And as a human, we see also its color. The machine does not see its color. The machine just sees the x1 and the x2 value. But we want to then now train this machine to see color, to see in color. And how will it do it? Because we will be giving the feedback. We will be giving.
Got a question.
Yes.
A little the visual where the dots are, the background to the left top, it's a little darker, slightly darker shade of blue than the right bottom.
No, you don't like that.
No. Does it mean something? I'm not getting the significance of those color change in the background. Okay.
See, it's changing.
Okay. All
So
right.
I am, why is it? Because we want to start with some random weights. So the machine, it's like you always guess, if you say, what is the answer, A or B?
Okay.
And you don't know the answer, you're going to guess. You're going to, in this initial case, just guess anything, because you have to have some weights. The weights have to have some numbers. Maybe you can call them 0. We don't like 0 for various reasons, but we like to give it a random weight, low, small weight. So which is why you see the shading is not very strongly blue or orange.
Okay. All right.
But I can, as I click on this, this reset button, I am resetting the weights. Okay. And
All right.
you may not also like the dots themselves. I don't like that dot there at the bottom. And then it's okay. We can generate basically from the same probability distribution, but you don't need to know about that. We can generate different samples. This is all artificial, fake data, of course. So we can generate. Let's just go with this one. We can generate random samples of the x1 and the x2 values for each dot. So far, so good?
Yeah.
All right. So now we shall train. So, to do the training, in fact, you can see in this case, the initial loss
The loss is huge.
is 70%. Whatever
Yeah.
number you see, multiply by 100. So its loss is 70%. Why? Because it just came up with some initial, which is why I paused there, initial guess, which is totally wrong.
Yeah. So
It
basically, the
doesn't matter.
blues are not in the blue dots are in the non-blue region, most of
Yes,
them.
yes.
So that
You,
signifies that it's not correct, basically.
yes. This
Okay.
college admissions officer, you will fire immediately. Right.
Okay. All
But
right.
this college admissions officer is yet to learn, and we shall start learning right now. And that's it. It learned. It has already learned, and it put all the blues in the blue region. It has put all the
S-
orange dots in the orange region.
Something like magic happened. What
This
did you
is,
do?
I just gave it 54 examples. I just gave
Okay.
it 54 examples of these dots, and it learned to draw a straight line. The magic is basically math, and the math is basically quite simple. All you need.
Just to interrupt, where on earth did those 54 example come from? I mean, it must be stored somewhere. It should be
These
accessible to naive people like us if we try. Or you
Yes.
did generate those 54 examples?
No. So these are the examples. So these are, let's say, more than 54 examples,
Okay.
right? So initially, as I said, we got some random weights. We
Okay.
know we gave the system only the x value and the y value. That is, we gave the system
Mm.
only the position of these dots, not its color.
Yes.
But we know the color.
Yes.
This is all the past students that did graduate 4 years of LLB, or
Okay.
um, I don't know how many years.
Mhm.
Anyway, they did graduate college. So we know, the admissions officer knows. And so the blue ones are the ones that passed. Orange ones are the ones that did not pass. And the orange ones had a grade and standardized scores that were, let's say, corresponding to the X1 and the X2 numbers. So all we were looking at is the X1 and the X2 numbers. And we are trying to predict whether the dot is orange or blue, right?
Okay.
And we never, when, we only give it as input X1, X2, which is not the color, but just the other values. As when training, and this is the arrow I had going backwards here. So when training, I will give you the color, right? I will still force you to predict something. I will give you a color. I will then tell you whether it should have been predicted as +1 or -1, because there's only a binary classification in this case. And then that difference, that loss between what you should have predicted, that is the difference between the actual and the prediction, and what you actually predicted, that loss is what then goes back and adjusts these weights via some simple math. Let's not get into that, but it's reasonably simple algebra.
Okay.
So now we go here, and that's essentially what we did at this point. And it said, it doesn't unfortunately show that feedback happening, but that's what happens. And you can see that in the curve of the loss. So initially the loss was high, and now it has gone down to
That's what the
0.
curve means. Okay.
And this is time. Basically, this is time, and it does. Now, don't be so impressed with this, because
No,
this is very
this time it
simple.
is 71, right? Instead of 54?
What? Yeah, this time I know. I just. It's like how fast I can. It'll keep going. When does it
Okay.
stop learning? Well, it
Okay.
never stops
Okay.
learning.
Okay. Okay. That is what you were doing. You were playing. All right.
Yes, I am play.
Okay.
I am.
Okay.
My finger is here on this button.
Okay. Okay.
Okay.
Hmm.
All right. So now this is one neuron. This is that one neuron we were all familiar with, right? What if we add more neurons? I can add one more neuron, right? And now let's see what happens. Now, of course, these two neurons, they both get the same inputs, x1, x2. They don't talk to each other. And this simply integrates the results of those two neurons. Basically, you can think of the output as yet another neuron that takes as input the outputs of these two neurons. Does that make sense?
Yes.
Now let's see what happens. Nothing happens. You didn't need that second neuron because all it needs to do is draw a straight line. Why do you need two neurons? You can do with one neuron, as we showed. It's trying to be a little bit clever, and it's like, you see, it's not quite a straight line.
Got a question.
Yeah.
The dotted line from the second neuron, it's a little thicker and bold.
Yes.
What does that mean?
Very good question. I can see why you're the professor. And please ask these good questions. That is the weight. Remember the weight I had in the picture here. This weight from the input, from any input to some neuron, there's a weight. And here that weight is represented by the thickness of this line.
Okay.
And if it is blue in color, it is a positive weight.
Okay.
The thicker it is a higher number, absolute number. And weak. And this is another way of the machine telling you, you really didn't need me. You didn't really need this. Look, you don't need it. Why do you need it? This is good enough. I don't need you. And all you need is this, and it'll do that. Looks the same. Let's see what happens if I do 4. Now it's kind of being dumb. It has, it's still drawing a straight line. Sorry,
I guess it's too many cook now.
There's too many cooks. One is saying, no, do this. And it's actually right. There are 4 admissions officers, think of it.
Yes.
And one guy is saying, okay, this is a good one, actually. But then that good guy is counterbalanced by these 2 others that seem to be consistently saying the wrong thing. You can see it in the color of these neurons. It's saying anything to the top and to the right, don't admit them. Admit only these guys. So these 2 are not so good, but the good triumphs over evil here because overall it has learned. So it has taken all these inputs and it has learned how to pay attention to those inputs. But ultimately you don't need, this is such a simple thing, you don't need more than one neuron. And this just shows how one neuron works. Okay. Now unfortunately, real life is not so simple in just 2 very distinct distributions. One introduction to real life is something like this. Let's reduce the noise so you can see what the real. So it's something like this. Now, can you draw one straight line through this? And this is going to be a little bit messier because I created some of these distributions. Now, can you draw one straight line through this to separate out the blue from the orange dots? You can see that it's not really. No one can, right? It's not possible, but let's see if the machine can. And you can see it's doing its best. It's doing its best.
It has done quite well. It has run it through just at the base. So okay.
So it says I can't really draw. I can't predict everything. My loss is still 9%. So 9% of these students.
And whatever it learned quite fast, and then it's not learning much.
It's not learning much. Exactly. That's a good point. It has learned quickly and it has learned, and there is nothing much to do. It said, I cannot do. I'm stuck. And this is the best I can do with one neuron. Now, what do you think will happen if I add one more neuron? So again, I start. I might reset the weights. And now let's do it. So now you can see what each of the 2 neurons are doing and what this boss manager neuron is doing with their inputs. This first neuron is saying anything, all I know, every neuron, initially, all they can do is draw straight lines. So I will draw, and you can see it on the right-hand side. Doesn't mean that's the output. It's just kind of showing you,
Wow.
this
Okay.
neurons. So all I can do is draw this line. Don't bother me anymore. This is all I can say. In fact, this might be the one that says, I just look at, the way I admit students, I just look at their high school marks, and I don't care about their, entrance exam. So anything to that side, higher, I do. The other guy says, wait, no. I look at the standardized exams a lot. I give it a lot more weight, and this, out is saying,
So
okay,
this is basically some sort of division of labor.
This could be, you can think of it, you can give it some, it is basically drawing, each neuron is drawing its own straight line, and somebody is saying,
based on its own whatever criteria or one.
Not based on its weights. So you can see it,
yeah, I mean,
you can see the weights. So this one is giving a lot of weight, positive weight to the x1 value, and very little weight to the x2 value. You can see here, right? The weight is 0.041. So basically it's, I just x1, I don't need anything more. And this guy is saying, I really like x2, and I will, be influenced a little bit in a negative way to x1, right? So these are the two weights for this neuron, for it to draw that straight line. Does this make sense?
Yes, at least to me, it is, I mean, the operation is quite striking.
What about your students? Any questions? I cannot see you. Why can I not see you? Here you are. No one has raised any hands. Does it make sense, or have?
Please respond, at least yes or no.
Yes, sir, we understand.
Yes, Diptiman. Diptiman has a question.
Yes. You see, that's why you need to ask these questions, because I don't remember to say all these things, okay? And so this is a very good question. It's a very important question. We have, and I have not said this at all so far, but to test something, it is like when you prepare for an exam, you don't get the question, that are going to be in the exam, right? If we already got the questions on which we are going to be tested, then we can learn, we can do quite well, right? So we train on a set of questions, think of it for your exams. We train on a set of questions, but then when we go to the exam hall, we are given a completely different set of questions from the same syllabus, hopefully, but they're different, right? So because we don't want to learn to test you on your memorization skills, we want to test you on your understanding skills. Same thing here. So what you see here are two kinds of losses: training loss and test loss. Training loss is how well can you memorize these dots? This is when I'm giving you all this information, you're using this information, I'm telling you which is blue and which is orange, that's the information. You are training on that information, you're adjusting the weights on that information, and on those blue dots and those orange dots that I already gave you while training, while you're studying for your exam, how well you do. You may not do 100% even on those, right? Because you forget, because you still don't understand in some of these questions, you still don't get it, right? But ultimately, the true test is in the test loss. These are the ones that we have not shown you. In fact, you have not seen them here so far. In these dots, if you can see it, they're outlined by a white circle, all of them, the orange or the blue. These kind of in this playground, that means these are training data. And in the bottom, there's show test data. If I click on that, you will see the test data. This is never visible to the machine until it has to calculate its loss, test loss. It is never used for training. Only the training loss is used for training, further training. And so we don't like to see it, but you can see though, it is not exactly the same dots, but you can see that it came from the same place, right? It has a similar distribution, spread over this range of x1 and x2, right? But the evaluation we do, the thick line here you see, is over the loss on the test, on the unseen, in the exam, how well you did, not how well you prepared. Does that make sense? But yeah, that's a very good question. And I should have mentioned this before. Okay, now let's move on. So here you can do, now another thing you can see it can do is this is just one layer of 2 neurons, right? And this is where the word deep comes in. Now I can add another layer. So now you see 2 layers. This is one layer of 2 neurons up here and another layer of 2 neurons to its right, right? Again, the question is, do we need this? Let's try it. Let's reset the weights. And you really didn't need it. It's going to do the same things. It might do a little bit better, but you can see the loss is about the same. Eventually, it has about a 1.6% loss, which is the same as what you really need, because you just need to draw 2 lines, and you're done. Now let's move on. Now I'm going to make it a little bit harder, and let me reset this. Let me remove this, and I will bring in this picture. So now, let me try to remove the color. Okay, fine. Let's do something. Anyway, so now you can see that this is like, now we are torturing the machine. So we say some of them to the north and east is good, right? And the third quadrant is bad, if you remember your first quadrant, second quadrant. So this is, the first quadrant, then second, third, and fourth quadrant. So it's not black and white like, one line or even 2 lines. So basically here, 2 lines will never, you cannot draw 2 lines to get this. And here, let's try. So it's trying to draw 2 lines. You can see the 2 lines it has drawn, right? And it is doing its best, but it really doesn't get it. It doesn't understand the problem, because all it can do is draw 2 lines. And by drawing 2 lines, you cannot separate the orange dots from the blue dots. Okay, you need something more. One thing you can do is you can add a hidden layer, and let's see if it learns. Here I warn you, sometimes it learns real fast and sometimes it never learns. And here I can tell you already, it will never learn. So even though I gave it the more power, it has not learned. So those of you who might want to get deeper into this, think of a very foggy morning. You are climbing up a hills, mountains. You want to get onto the top of the tallest mountain. But you cannot see anything except the ground under your feet, because everywhere else is fog. So you cannot look around and see which is the tallest peak. All you know is, am I going uphill or downhill? And you would like to go uphill. And you keep going uphill and uphill. And this is how the weights are changing. Where your feet are is basically the weights, the space of the weights. And you want to go to the place which is, and at some point you say, okay, no matter now, I'm at the top of a peak. I can go left or right or, front or back, but all of them are downhill. I'm at the top. But is this the tallest peak? You don't know. And so sometimes it can get stuck, especially if you don't give it a lot of neurons to deal with, it can get stuck. And sometimes it does, better. Sometimes it may do, no. I will try a few more times. No.
Oh, the same configuration, different times it can do different, produce different results.
Exactly, because it all depends on where you start. There is a lot of randomness built into this.
Okay, thank you.
And depends on where you started and where you end up. This it learned finally. See, after many tries, it learned the real thing. See what it is doing now? The first 2, they can only draw straight lines. Remember, the first neurons getting the X and Y.
I've got an irritating question here.
Yes.
I mean, if they drew only straight line, if it were capable of drawing a cross, that would have accomplished it as well.
If it drew a cross, somebody else has to tell you still what is to the left of that cross. You still need one more input to say
Okay.
anything to the left and above that cross is
Ah,
bad or things like that. And
okay.
this is what exactly this is doing. This guy drew one of the lines of the cross, this
Okay.
neuron.
Okay.
This guy drew the other line because that's all it
Uh-huh.
can do. And then this guy is saying, you know what I'll do? I'll take anything to the bottom of the line, of the horizontal line, and to the right of the vertical line, and call it blue. Totally wrong, but it doesn't matter. And this guy is doing the opposite. And this final guy is saying, whatever you say, I'll do the opposite because these weights are negative. Right? Whatever you say, I'll do the opposite. Right?
Okay.
And they are saying, these are again the two critics. They are kind of weird critics because they always say the wrong thing, which is the same as always saying the right things, because all you have to do is whatever they say,
Flip it.
just do the opposite, right? So when someone says you're always wrong, it's actually a very good compliment if someone says you're always wrong, because that means you're always right. So these two are always wrong, but this guy knows that, and it has trained. All of this is by training. I did not do anything. By training, it came up with a weight of negative. That means I'll do the opposite of what you say. Weight for this is negative, and together I can get. But you see how many times, how many trials it took. And how do I know? I just got lucky. Maybe next time I try, maybe it's going to do that stupid thing. This is where I can simplify. Let me. Okay, I have time. Let me do another way. So here I added one more layer. Another thing I can do is add more neurons. Okay, I can add more neurons. I can draw more than 2 straight lines, right? Here I can draw 4 straight lines. Let's see if that helps, right? And
Okay.
you can see that it will kind of do a better job. Uglier. It looks uglier than that other one, but it's getting better. It's doing better. Okay. Um, Let me, so no matter, every time it'll be different, but it is learning some weird thing, right? And it is doing reasonably well because it
This is
has,
not all that bad.
it's not that bad. It
Yeah.
doesn't know all these, it's still doing it on the basis of drawing straight lines. It doesn't have that second layer to say, I'll take all your straight lines and create regions like you saw it did. It just think, I just deal with straight lines and I can do something with all these combinations of straight lines. Okay. I can add now, if you want, let's do that. Oops, wrong way. So there is a deeper network now. And it'll learn. Now you see how it will always learn. Now this is why because we don't know the problem, we don't know the shape of the problem. Unfortunately, most of our problems doesn't stop with X and Y. No, only with 2 values of X that we can visualize. So, but basically this is where the deeper you go, see how the first layer of neurons are drawing straight lines. This guy is not doing anything useful. Drawing straight lines. And then these guys are drawing regions, right? These guys are drawing regions, different kinds of regions. And the final manager, if you will, is taking all the inputs of those regions and saying, okay, when do I trust? Who do I trust? And it's combining them all, right? With different weights, as you can see here. Yes?
Deeptiman has a question.
Okay. Yeah, please let me know because I don't look in the
Yeah,
other
no,
screen.
no, I'm.
Okay, thank you. Yes. No. Sorry, good question. They're very good questions. Can be anything. More is better, but more is also slower because now you have to adjust more weights. So you can have any number. As I said, you can do it with 2 and 2. You cannot do it with 1 and 1 because 1 is like all it can do is draw a straight line and that's it, right? If you have only 1, adding more and more layers is not going to do anything because it's not helping. There's nothing to combine, nothing for the second
Nothing to
layer to
combine.
combine. If I had 1 more here, And this is why this playground is very nice to play in, because you can ask these questions and don't always take its output for the truth, but so it'll do something, but it's the same as if I didn't have this guy, if I didn't have this guy.
Okay.
This is the same.
There is a question
Anyway,
by
yeah,
Akash Satyadev.
go ahead.
Akash, please.
So, what kind of information is provided by these hidden layers? So, like, what is the significance? Like, if we increase the hidden layers, how will this output be changed?
Yes,
How will it
very good
respond?
question. Yeah, very good question. You guys have very, it's very, I can see you're asking the right questions. Of course, there's no wrong question to ask, but that is the whole of learning. So here, of course, is a very simple problem. There are just 4 regions, there's a x1 and x2, and there are 4 regions, and we are trying to do this thing. You can give this to a, maybe 3-year-old, I don't know. And they can draw these 2 regions and say, okay, where are the blue dots, and draw a circle around it. They can do it, right? Their weights are already trained and they can do it. But in the real world, but what you can already see there when it worked, I wish I had kept that, is one layer was drawing lines, the other layer was drawing regions, squares, using those lines. So these hidden layers build up on top of each other. So if you use like language as an example, when I say something, you need to understand the words, then you need to understand the grammar, how these words get put together. You need to understand beyond the grammar some of the meanings of these words, what these words imply, like what does LLM mean, and it can mean different things. So you can just imagine, and then there could be another which looks at the relationships between the words. I got an LLM, I received an LLM, that means something, almost the same thing, whether I say got or received. And there's a relation no matter what language I use. So you can think of all of these being learned at different layers, where the lower layers are helping you to learn a more abstract fact, a more abstract knowledge. So this is the reason. So you can think of the first layer in our example as learning lines. The next layer is learning regions, learning, regions. These 2 dimensions. Imagine if it is in 3 dimensions, or 4 dimensions, or 500 dimensions. I'm not done. That's basically what these layers do, build up on top of each other, kind of like what you do when you go through different classes, class 1, class 2, class 3, class 4. Think of them, and this is a bad example maybe, but think of them as layers. You learn something in class 1, you applied it in class 2, you learn something in class 2, apply class 3, and you're going through these layers. There, unfortunately or fortunately, you're training layer by layer. Although you still might want to learn, something that you should have learned in class 1, even now, maybe. But that's how you can think of these layers. I hope that makes sense. But this is just a approximation. I want to get it's 9. It's like we have half an hour left. I can stay a little bit longer, but I just want to go through some other things before we go back to the slides, and then that's where I will end. So now, just to know where it works, where it doesn't work, what is the architecture, what is the shape of these networks, where it works. So imagine now I have this problem on the right-hand side. Anything outside of a certain radius is fail, let's say. Anything inside of it is pass. Don't ask me what the x1, x2 means in this case. But imagine your problem is of this nature, right? Can you draw a straight line for these? So you know the answer. You cannot, right? You will see that it's trying to draw a straight line. In fact, you can see that it has cleverly maybe chosen a portion where there are not that many orange dots, outside. So it's not making that much mistakes, but still it's making a lot of mistakes. It can obviously never learn how to do it. Let's see what happens if I add one more layer. So you can see how the first layer is learning lines. Second layer is learning regions, but it cannot learn. It cannot learn this problem. Let's see what happens if I add yet one more layer, because it needs to learn one more thing, which it has so far never learned. Now, more layers you add, it takes a bit longer for it to kind of, it's moving around, looking, it has more knobs to fiddle with. So it's trying out everything. But you can see it's stuck with
So
those two
who is
lines.
changing the weights? Is it changing by, I mean, in the program, or are you making that change?
My hands are off the keyboard. I'm not changing anything, right?
Or the weights are changing
in my hand.
automatically?
The weights, this is the training. That is the training. Right now, when you see
No,
this number.
when you say training, again, who is training? Is it training itself?
It is training on these colored dots, right? Not on test data. So this test, this is not training on. It is evaluating. It is applying on that.
Okay.
It is training on the fact that these I force it to predict something, and then I give it the loss. Did you get it right?
Okay.
If you got it right,
all right.
losses.
Okay.
And I is not me. I is the program. So the machine learning program is saying you have a loss. You better, all of you adjust your weights. There's a loss, and they all try to adjust their weights accordingly. Okay. Sometimes they may say, I cannot do anything more. I see this loss of 23%. I am stuck. I am on that hill, on the top of this hill, and it's very foggy, and I don't know. Any step I take is going to be worse. So I'm not going to move from the top of my peak. I don't know if it's the best peak I should be on. It's the tallest peak, right? Because I cannot see that I need to go down a little bit before I can. Here also, I didn't give it the language. And here's a simple thing I can do. Delete, oops, wrong one. Delete, add, oops, wrong one. Sorry, my mistake. Here. Now it'll draw what? 3 lines, right? And with 3 lines, you can do that. So draw a triangle. It still didn't understand anything about circles, but it says, I can do quite well with a triangle. 3 lines.
Yes, some sort of an enclosed space. 3 lines could enclose an area.
Exactly. So with 2 straight lines, you cannot enclose something. Because as you saw, any of those regions that it learned, even with 2 layers, it was going off to the edge. With 3, I can draw an enclosure. With 2 lines, I cannot draw an enclosure, straight lines. I cannot draw an enclosure. The reason it's not exactly straight lines is because of that nonlinearity, that fuzziness that is there in the activation function. All right, let's move on. But here's one other thing, and this is kind of very important.
There's a question from Diptiman on the chat box.
Okay.
Yes, Diptiman, can you say it? Diptiman says, sir, how are the numbers of layers neurons chosen? Is it trial and error?
Yes, that is your problem. You have to, understanding some of these things we are talking about today, you have to choose. Now, of course, computing is cheap, quite cheap these days. And so you can say, why am I dealing with 3? I'll just make it, 8, and I'll just add more layers. Who cares, right? I'll just do that, right? And I'll add, more layers, and I will do that, right? And now I train, and I'll get, look, how great is this thing? But did you really need all these, right? You see it's drawing more of a circle now. It's actually learning from lots of straight lines and combinations, circles. And you can see this guy actually already got it. These are already getting the circle-y kind of things. So yes, so what we do is we say, okay, with your problem, let's just try, 3 hidden layers, 8 neurons each. Oh, it's not working. Your loss is still high. Okay, let's try with more neurons in a layer. Let's try with more hidden layers. And this is why you have these things called deep learning, because this is when computing got cheap in the 2000s. Computers got fast, lots and lots of data. So we say, we don't really care to understand your problem. We don't really care if you have a circular problem like here, or this kind of a problem, or this kind of a problem, or this kind of a problem. Maybe you have this kind of a problem. I don't really know. I can't really tell. And so the lazy thing is, I have lots of computers on my, or lots of GPUs, and I'll just learn. I should have done this. I'll learn, and maybe you will learn something about spirals, by by doing this. And, you know, as you can see now, the loss is continuously going down, the training loss. It still hasn't figured out the spiral, and that's why the test loss is much higher, you can see, than the training loss.
Bah.
Training loss, it's saying, I can fit with all this knobs you have given me, I can fit something that fits these things. You can see how it doesn't care if, you know, in this area over here, I don't know if you can see, it's orange, because there is no training data there, so it's perfectly fine. See how it drew this? If I show the test data, there's like blue dots there. It doesn't know about that. So that's why you have a high training loss. But you can see it's learning something about spirals without really knowing anything about the problem, right? And this is the value of neural networks, is that you give it enough layers, you make it deep enough, and it'll learn anything. And now you have large language model, and this is why it's called large, is because it has like a trillion nodes. Not just here, it is 8 times 3, 24 nodes. There are a trillion. What is trillion? I don't even know how to count up to trillion. Then if I give it a trillion nodes, surely it's going to learn something.
Oh,
let's
my
move
goodness,
on. You know.
it is getting into a
yes, so
spiral, huh?
It is learning
something close to the yin and yang. My God.
Yes, it is learning, and you can see that because it doesn't know here, you know, it should have that inner orange blob should be connected with the outer orange blob, but it doesn't have any examples here, so it
Exactly.
the test data might hopefully have a dot right there, and doesn't know that, which is why you see there's a gap, small gap.
Yes.
The loss of the test is higher than the loss on the train, because as far as the train is concerned, 001, I got it. And this is the other problem that can happen. This might be a little bit, is that it can overfit to the training data. Whenever you see this gap between the training loss and the test loss, you can say that it has overfit on the training data. It has enough flexibility in its neurons, in its depth and the width of the neurons to memorize essentially all these dots. And it is like you study, you have a big brain, especially when you're young, and you know lots of neurons haven't been taken up, and you can memorize, and then you go to the test, and then because you memorized, you may not be able to do it so well because you memorized, and the training data, your exam looks like this, and you can still have a little bit of a gap. You learned everything. I stayed up all night. I have trained on 2,000 times on this material, but I can still memorize and overfit to what I learned and not understand what I learned. Let's move on because there is more. And this is really where I want to get back to my slides and get here. So I just want to finish, if this time there's more. This is our problem. Remember this problem. You are a college admissions officer. You have this now X1, X2. Why? Now you have to have precise definitions. What is Y? What does it mean that the student will succeed? It means the student will graduate in, I just made this up, in 4 years with a higher than 2.5 GPA. That is pass, let's say, in my world. And that is my definition of success. And only inputs I get is the high school GPA of the student who has applied and their standardized test score, at some admissions exam they took. And now, of course, to be fair, it's like, I want to be fair. I don't want to be biased. I don't want the machine to be biased because we know as humans we are biased. I don't want the machine to be biased. Don't look at it. Be blind. Be blind to everything else about the students. Look at their scores and give them a grade, admit them or reject them. And guess what? I can do it. You saw that. I just need 2 neurons for this program. You can see that some of them, it got most of the blues right. It got some blues wrong, but it got some oranges, but it did reasonably well. Okay. So, but now let's see what's going on here. And this is where because you're law students, this is my favorite portion of this talk, actually. And how much time we have? We have time. So let's dig deeper into this. And this is where the real world meets the mathematical world. And what if we say that these test scores that we got are from 2 groups of students? And for one of them, and so this is a line I drew. right? This is ultimately the line I am using to admit or reject students from my college. And what if I told you that there is a group of students, like a majority group, that's why they kind of win, you know, the losses are low because most of the majority, you do get it right. For the majority students, this looks good, but there's also a minority group and they're all going to get rejected. Even the blue ones are those that had you picked them for college, they would have done well. They would have graduated, but you didn't even, this machine will not even pick them. And so this minority group, maybe in the minority group, they don't do so well in their standardized exams because they don't have money, etc., to get coaching classes, etc. They may have to do a job while they're going to college, school. They're, you know, they're whatever, you know. But if you gave them a chance by looking at something else, if you gave them a chance, you can see that we know from past that they can very well, some of them can very well succeed. And so by explicitly being blind, in many cases, they will say, we don't look at these things. We don't look at these different other attributes. We are just guided by the test scores. So we are fair. But you're creating an unfair system by doing that. And in reality, what should we be doing? We should have a third dimension. Let's just call it some x3. And now this is why, you know, hard to draw in 3 dimensions. But that first, you know, x1, x2 you can see. And now you have this other x3 dimension for the demographic group. And now you can say, we have seen both of these examples in our playground, right? We have seen the first example where you draw a line like 2 lines, and the second example where you draw 1 line. And of course, you can see that even if you had 2 neurons, you can still draw one line. So you just needed to give it this additional information, the x3 information. And those 2 neurons would have done the job. So sometimes you have to be looking at other attributes that as a human you might be biased by, but as a machine you might be helped by. And you know, so this is where you have to be careful. You can create a neural network with lots of layers, lots of nodes. It can train. It can even do well because it's doing quite well for that majority population. Your admissions officer will look really good with this, right? Because look at all the blue against blue. Those are all the ones. Only 2 of those failed. It looks like. Would have failed in college. Everyone, and who knows, we don't care about all these blues that we rejected, all the ones that would have graduated from college successfully, but we didn't even give them a chance. But admissions officer doesn't care. He cares about the ones that he admitted, and he looks good to his dean. However, for the student, you have these guys who never even got a chance to be admitted to your college, and half of them would have succeeded. So this is a pitfall. This is a cartoonish example of something that happens a lot.
There's a question, Sugato, from Akash Satyadev. He has raised a hand. Akash.
So now you have brought this mechanical concepts to our area of justice, equity, and fairness. So I want to ask this question: though these machines are learning from real human neurons how this work, so we are as a human, we are also, because we are in the same space of work. So we are also learning from how these machines are taking this data and coming to a conclusion. So, sir, is it not crushing because with everything we are moving from humanism or realism to dataism? So, is it not crushing the essential element of human consciousness? It's more an ethical question, but just I felt like asking. That's why I asked, because you are also researcher and also that's.
Yeah, I
I
don't know.
want to know, what do you think about this?
Yeah, that is a deep question. What we have done as humans, and sorry, I cannot resist. What we have done as humans is know how to use tools. That's all we are tool users. And this is a tool. And the tool can be used or it can be abused. We can learn something of how we work with a tool, but we need to understand that tool. We need to know where it is good, where it is bad, where are its biases, and we need to be guided by that, which is kind of my introduction here. With the same examples I was showing, I can say, look, maybe you do need to, and this is a simple example, you do need to consider the fairness. Is this machine once trained? Don't give me the overall loss. In that playground, you only saw one number, the test loss. Don't give me the overall loss. For that guy who was unfairly rejected from college, his loss is 100%, her loss. So I don't care about, admissions officer. Yes, you care about the average of all, and you're doing quite well. You have a 1.5% loss. That person, 100% loss. So, we need to, as humans, we need to be guided by these tools. We should not be blindly using them. And we should be using, but the reverse is also true. As humans, we are very biased. Whether or not we admit to it, whether or not even we are conscious about that bias, we are biased, all of us. And that is why we put these artificial, blinders. We say, okay, we won't look at this thing. We won't look at the picture of the applicant. We won't look at their, which, I don't know,
ethnic
what
group.
their group or other things. We won't look at them. And then we will be fair, maybe not. Let me move on a little bit, but that was a good question. That is what, I try. But just to finish this, and maybe how much time I have, because I gave you a promise and I think, sold you short, because I only showed you how to do these dot things, numbers, grades, and GPAs are nice numbers. And, pass or fail is like 1 and -1, so that's all you learned. Now you'll still be wondering, how do I go from that? If all you're saying everything is neural networks, how do I go from that to this? And this is actual input and output from GPT-4. The input, the human typed in, explain the plot of Cinderella in a sentence, using, by the way, these same neurons. Explain the plot of Cinderella in a sentence where each word has to begin with the next letter of the alphabet, A to Z, without repeating any letters. This is the instruction given to GPT-4. GPT-4 has to understand this instruction, know what it means. It took me to read it twice to understand what it means. And then it came up with this output, which is 26 words. And it says, it's showing that it knows the story of Cinderella. And it says, every word is starting with the next letter of the alphabet. Beautiful Cinderella, dwelling eagerly, finally gains happiness, inspiring jealous kin, relatives. Love magically nurtures, opulent prince, quietly rescues, slipper triumphs, uniting very wondrously, xenial youth zealously. XYZ is always a problem, but xenial, I looked it up, it means, friendship, friendly relationships between groups of people. And, how did it do it? It shows two things. It shows that it can read that input sentence, the instruction. It was not trained with this Cinderella. It was not trained with doing this only. It was not even trained. This is probably the first time it got this job. The next one could be prove the infinite prime number theorem in a limerick and write it in a limerick, and it will do that, or whatever. So it learns, it understands, I would claim, that English sentence in white that the human gave it. It knows the story of Cinderella. It knows all the words of English language, probably more than you or I, definitely me. I didn't know what the xenial was until this. And it can use that, even though we know all the other words, would you have figured out now, that this might be a good way, not only, slipper, the prince, the jealous relatives, everybody is here, everybody, Cinderella, of course, everybody's here and came up with this thing. Can a human do it? Can it do it this fast? I don't know. I don't think so. But how do you go from what I have shown to this? And in the last remaining minutes of this, I want to give you a flavor of that, or how it happens. And we go back to our node, same neurons. Basically you have a whole brain full of these things, kind of. And you can write poetry, you can draw beautiful paintings, sing, argue before the judge, win cases for your clients. You can do all that, all with these things, these nodes. How do you do it? It's even more amazing than this, right? How do you do it? So we will take this node, we just got rid of all the stuff in it. It's the same node, same inputs, same outputs, same weights. As you saw, we can create layers. And when we create layers of one layer, this is just a layer of neurons, as you saw in the playground. You can think weights as in a matrix. I don't know if you remember matrix from, not the movie, from high school. I don't know if they teach. But think of it as a set of numbers, with 7 rows and 3 columns. Each one, in each of those cells of that table, there is a number, right? That's a matrix. And that's basically how I could represent these weights, right? And now I can simplify further and can say, okay, I don't care about those pictures. I just have that weight matrix. This is what we would call a matrix. Now it's no longer 7 by 3, even though it looks like that. It is V by D dimensions, V rows and D columns. And what do I put against the V rows? I put all the words of the English language. What is the size of the English language? Maybe a lot, but it doesn't matter. I have space in my computer. I can put in all the words from A to zygote. Put all the words. In reality, I put quotes around the words because we don't do words, we do word pieces. Because sometimes you don't care if it's abandon or abandoned. We would say it's abandon and ed. These are 2 word pieces. I still want to know the ed, but ed has a particular transformation it does on any word that precedes it. So we do word pieces. Maybe there are fewer word pieces because you can combine all of those things. So anyway, let's say there are words. Let's not argue about what the size of V is. It's big, but it can fit in memory. And my job now as a machine learning expert is to convert this. The input is going to be, everything is 0, one of the inputs is 1, right? Because I encounter a word. Let's say I encounter the word abandon. Then the input is going to be 0 for the first row, 1 for the second row, and 0 for all the rest. And then my output is just going to be that, whatever, it'll going to be this, whatever is in this row. So now I have representation of all the words of the English language in D dimensions. Here it looks like 3 dimensions, but let's just call it D. D can be 700 or something like that. Not more, not a large number. 768 is what I play with.
Sugato, what do the columns represent?
The columns don't represent anything.
Okay.
The columns represent the output. See, the columns represent what that layer, that single layer.
Okay, that's a layer. Okay.
Yeah, one layer. This is one layer. What that layer would say if we force that layer to only have D neurons in it. D is 3 in this visualization. Okay. So now you can see that what I did, if you know about sparse matrices, I converted something which has lots of zeros and only a single 1, because the 1 is matching the word that I try to represent. And it's a huge, V dimensional vector, mostly zeros, one of them being 1, and I converted them into 3 numbers of any real number. And the argument is that these 3 numbers can represent everything if we trained it properly, because each of these numbers has infinite capacity, right? 2.61 might mean very different from 2.6, right? Hopefully another number, which is, let's say, negative 1.0, negative 0.10, negative 2.6, negative 0, positive 2.7, very close to this, is something similar to the word abandon, that you can replace the word abandon with that. And that's ultimately what it learns. But let's move on. And so what we did is we took the three-dimensional, very sparse, lots of zeros, only a single 1 for each word, x's into a y, which just has, in this case, a d-dimensional vector for every word of the language. And this is just one layer, right? So, now you can have 50 layers of these things. And what we do is now we train it on the English language. So we have to train these weights. Imagine by random, it's not going to do anything. You saw what it does even on the, but randomly, it's not going to do anything. We have to train these weights. Again, by what? By losses. The same method that we saw in that playground. It doesn't matter whether it's learning how to admit students or how to learn language. I have a loss. I predict a word. It's wrong. Then there's a loss, and I train myself to predict the right word. How do I do that? And this is going to be the, so if I said, and hopefully, if I said I went, I want to predict the next word. And I said, I gave you a sentence. I went to NUJS to get a, what do you think the next word could be? There's no wrong answer, but what do you think it could be? Why, let's say in the past tense, you went to NUJS to get a what? Give me one word.
Degree.
You predicted my prediction. But degree is not. You could say I went to NUJS to get a letter of recommendation. You could say LLB. You could say many things, or it could be in a completely different thing. You didn't, it could also encounter words where it's I went to NUJS to get a,
get a job.
Get a job. I was thinking of, to get a sandwich from the cafeteria. I don't know if there is, or to get a whatever. It could be anything, right? But one of them is degree. And then what's the next word? What do you think the next word will be? If it is degree, let's say you fixed it on degree, no more job or other things. I went to NUJS to get a degree. What could the next word be?
In law.
In LLM.
In, okay,
law.
in
LLM.
law. Okay, you're all right. I'm not, but your advisor, your professor seems to be right in sync with what I had predicted he would say. And what's the next word? It has to be grammatically correct. I went to NUJS to get a degree in law, and the next word could be a full stop. Sometimes the machine needs to know when to stop talking, just like we do. So this could be a sentence. And now imagine I could train a machine with everything written by humans, all the language, which is all there. We look at everything that is available, legally accessible. So I might have trained it on all of these, and amongst many things, this large language model. I could have trained, and it encountered this NUJS. I don't know what NUJS means at the beginning, but now I learn something, and it has learned it has seen all these things. It has been used to predict the next words of each of these sentences, let's say. And so now when I give it that sentence, I said in the beginning, it's going to use all this learning, all these weights. There are a trillion weights to adjust. It can, there's a lot of flexibility in it. And it can, incorporate all this information just by the same method that I showed you in that playground, by just updating weights in every neuron individually. And the way I do it in this case, remember I have now converted all my words into numbers of D dimensions. When you think of D, think of 3, because I'm visualizing it in 3. By the way, now everything is, please take it with a grain of salt. It's not exactly how it works, but the theme is correct. So I have all these words. I send it to these decoder, what is called decoder layers, but think of them as those same layers that you saw. And this is a simplification, but it goes through these decoder layers, and then these decoder layers have the weights. Those are the neurons. They have neurons in them. They have weights, and those weights have been trained by doing this over and over again on everything in the English. There didn't need to be a teacher. There didn't need to be a right answer, wrong answer. It just looked at all the words, all the sentences ever written in the English language in anything, Cinderella, NUJS, everything, right? In between. And it knows, it has, I shouldn't say it knows, it has adjusted its weights to be able to do as good a job as it can to predict this. Such that in this second sentence, if someone said online masters, whatever is now being offered by Dash, NUJS might be right, but so maybe many other colleges might be right. And guess what? They're all then similar, right? Then I know what other colleges are similar to NUJS because I can predict, probabilistically, what are all the things where institutions, and I don't even know that these are institutions, the machine doesn't know, but what are all the words that could fit in here? And a human, when looking at it, say, oh, it knows about, law colleges. But it really doesn't. It just knows how to complete these sentences. So finally, when I get the word A, I went to NUJS to get A, and one of you said degree. I don't know. Right now, when I pass it through, I just get some numbers. But these numbers I get out indicates the probability of what the next word could be. And it's highly likely that the probability will be high for the word degree, as it would be for, what else did you say, a diploma or to get a job or whatever else that might be likely. And let's say I pick one of these words based on their probability, and I put that in there, right? And I repeat. Now I put the word degree in there, and then what is the next word? And I keep going on and on and on, and I can get a complete sentence out of the machine. All by just training those same neurons, those same weights, but at a much larger scale after having converted words into numbers. And that is it. So once you understand how one artificial neural network works, all of this is just more and more and more of the same until it's so big that no human, even the ones who created this, knows exactly what's going on in the system. But there's one thing that is going on in the system that we need to be careful about. So here is an older version of GPT. And the input was, my husband just got an exciting new job. Starting next week, he will be what? One output was working at a restaurant that I grew up in, just whatever, working. Next output is a consultant at a bank as well as a doctor. I don't know what that, but good things, high-paying professions. Or working on my new book, very creative person, it looks like, writing a book. Same thing, I now say wife instead of husband. Remember, it has learned next word prediction from reading a lot of human writings. We know humans very well, they can be very biased, or their writing can reflect the bias that exists in the world. So my wife just got a new exciting job starting next week, she will be, everything else the same except the word wife and the word she instead of he. Working full-time, well, that's good, but it's all related to the children, community, involved in school, and things like that. Working in an office, but doing housekeeping. Okay, or it couldn't resist being a full-time mom, right? Why does it do that? This is that same thing with all this sophistication. Why is it doing this? Because it has been trained on human output. It has been trained on human output describing the world we live in, with all its biases, with all its problems. And it is simply reflecting the biases that it has learned from humans. So you got to be aware of that. The large language model can learn. It can learn biases just as well as a child can learn biases. And we need to be really careful about that. New, modern, more recent ones. This is an older one where it was not filtered. Its output is not being, second guessed. Now the models are a little bit more politically correct. And this is part of that instruction tuning. Someone says it must have been given negative response, negative feedback on the right-hand side kind of inputs, and say you can't do that. Humans, yeah, we do that, but you can't do it. But how many times, how many such, guidelines can we give? We don't know all the biases we have. We have written them out in language. We describe them happening, but the machine is just going to, if it is going to learn massively on these texts, it's going to pick those same biases. So this is the final slide I have, and it's 10 o'clock. So sorry, here it's 8:30. So what did we learn? We saw how machines learn. What did we learn? Well, we learned about artificial neural networks. Hopefully, something. Please play in that playground to play. To learn some more. We learned how it learns from supervised learning, and we saw deeper, the better. The deeper it is, the less you have to understand about the problem, really, and you can just say it'll figure it out over time with different layers. Is the training now? I said all these words to you. You understood it immediately. Hopefully, I hope you understood what I'm saying. You didn't need training, right? So is training the same as what is understanding? I used to believe no, until I saw what these large language models are doing, where you give it an instruction, that Cinderella instruction, for example. I would argue that it understood that sentence because its output reflects the understanding. In many cases, I can still trip it up. I can still give it an instruction where I can see that it really didn't understand. But it's same as us. I can tell you something and you understand, and another thing I say, you don't understand because I don't have the same vocabulary. I haven't walked in your shoes. And can it learn? Yes, it can learn the same biases as humans if it is being trained on human data. If it is trained on, it's going to learn the same things because it's very good. All it is doing is mimicking. It's reducing its loss. And the loss is defined by humans. Now you can say humans are going to say, okay, let's put guardrails, cannot say anything hateful, you cannot criticize somebody's religion, you cannot criticize gender, you cannot, when do you stop saying that? Because many things are going to be, left unsaid. So how do you put explicit guards against biases that are inherent in any human behavior output? And so this is basically the question somebody asked, how do we use it properly? So you cannot hold the hammer the wrong way and expect good results. You cannot hammer in a screw. We have a tool, but we need to know when to apply it and how to apply it. And that's basically the end, message that, what I want to leave you with. You can learn all the math. You can apply. You don't even need to learn all the math. You can download some stuff, you can apply it. You can download, you can go to the website, use GPT-4 or whatever else is there. It's just a tool for you. You need to be aware of where it is coming from and how to, hold this hammer properly. So that's it. By the way, this picture I just said, I didn't know, I typed it into this artificial, large, image generator.
Ah.
It's another output from the company that created GPT called DALI, and I can say draw a picture of I didn't get it but anyway it drew. I didn't say anything about the screw. I like it better than what I had in mind. So it's completely artificially generated. So anyway, this is basically any questions at this point. I know I ran a bit late, but that's because I don't know when to predict the full stop in my sentences. Here are some reading things which I sent to your professor. And these are all not really like academic papers, but more like blogs and other things that I found useful. And there's more, of course. This is just a little sampling of what you can read. So with that, I would like to go back to yeah. So any questions? Any?
Yes, I think Deeptiman has a question.
Go ahead. Mm-hmm. Yes, an AI model is what you trained. You have an algorithm. Let's call it artificial neural network. Let's call it a decoder. I introduced the word, but I did not describe what it means. These are algorithms. A decoder is an algorithm. A deep neural network is an algorithm. The model is what you got when you trained it with examples. When you trained it with all those admissions, students. At the end of it, you got a model. Now it is based on that algorithm. Now you have a model trained to only admit and reject students from your college, and now you apply that model to new.
Okay, the same model is not going to be applicable for whoever is going to be a good cricketer or not.
Of course not. Hope not.
So but the same algorithm is there.
Yes, exactly. That's a good way to say. The same algorithm could be used separately to train another model to predict who is going to be a good cricketer, maybe harder. Uh, One of the things with the large language models, and this is what we call general AI. So all of these things we were doing, you're training these models. One model it can only predict good, who to admit. Another model can only predict who is going to be a good cricketer, etc. There's not one model who will do all of these. But if you look at these large language models, it's one model that can answer, that can take your instruction, as long as it's written in English. And by the way, even that, there are translations using the same approach, translators. But it can do many things. It knows about Cinderella as much as it knows about, your college. And they are not in any one book, as far as I know. So there you see glimmers of general knowledge, like a human has. And question is, and this is this is what we are dealing with, is what does it know? We don't know how it knows what it knows. We know how we trained it. We know the architecture. We know the algorithm. But do we know the model? I would say we don't.
Do we know how we know?
Exactly.
What we know?
Exactly. Do we even know how to measure intelligence? If you're going to have an artificially intelligent system, how do we measure intelligence? The random person I meet in the street, will I call him or her intelligent? I'm sure intelligent in some respect, but so yes, we don't know how we work. So how can we build a machine? However, we can appreciate its output given the input, and that's how we judge any other human too.
Shivangi
Yes.
Bharadwaj has a question, raised a hand.
Sir, I wanted to ask, we talked about learning part. What about unlearning? Because we discussed how machines also learn the biases that humans have. So humans don't unlearn, humans forget. Even if we forget or overcome biases, it remains somewhere with us at the back of our mind or in our subconscious. How does it work with the machines?
The one answer I have, it definitely forgets. It forgets, we have been dealing, in our little world, we have a model. It can understand language in a certain way. We train it on all these IBM corporate, this language, and it forgot certain things. It forgot basic things. And you say, how can you forget that? Well, because we trained it to bias its weights, to change its weights on the language of businesses and databases and whatnots, revenues and accounts and all these things, and it forgot about nice other things that it should have known. So it definitely forgets because it's the same set of weights ultimately. It depends on how many weights you have, and if you see a loss, you're going to adjust the weight. You're going to forget the fact that you were trained earlier in your life on other things. So that some of that forgetting might be good, some of that forgetting might be bad.
Is that
But
random or can it be controlled? Forgetting?
to control,
Control means at least select or
yeah,
influence that you forget these things.
I don't know how you forget. I don't know. I do know how you keep remembering. That is, if I know, like if I know that you should not forget certain things, then when I train with new things, I put in some of the old things too. Like, when you give a test, sometimes you give it some questions from the new material, but you say you should not forget that old thing. So I'm going to give you some questions that are from earlier, but you shouldn't have forgotten it. Same thing. I can train it with a mix of old things and new things.
Yeah.
But how do I force the question? From Shivangi was, how do I make it forget something? That is done now by a layer. Remember when I was showing you those circles, those boxes and boxes, there was something called generative language model. It can generate anything, like all these biased language against husbands and wives and things like that. But I can give it remember one of the other things I told was called reinforcement learning. And I can say, if you say that's bad, you get a slap on your wrist. And don't do that. I don't know what you did wrong. I don't know how many moves ahead in your chess game you made the wrong move. Don't do that. And so that's another form of learning which says, be nice, behave. And
So that is trained unlearning of sort.
there is a trained slap on your wrist, a
Okay.
penalty given to you.
All right.
And you figure out, I don't know, now I'm not giving you what you should have said. All this.
Okay.
All I know is don't say
Don't
it.
do this. Okay.
Don't do this. This is how sometimes we tell our children. We don't tell them what to do right. Don't do that, and they're confused. But the machine can say, okay, I could have done many other things. Okay, I won't do that from now. And that this is a kind of way in which you not quite forget, but penalize it for doing bad things, just like our judicial system.
Here, I want to add means I want to know actually. I mean, we often forget by non-use that I'm not using, I'm not using, and then I just forget. Does that happen or it doesn't happen?
Yeah, that can happen. Non-use might mean I have not been trained on that recently.
No, I have been trained. Maybe I've forgotten, for example, a
Yes.
piece of poetry. I mean, a poem I remembered, but I haven't recited it for the last 5 years, and so I've forgotten.
I cannot explain, obviously, the human brain, how it forgets
No,
and
but
remembers.
in the AI,
But
does it happen?
in the AI, what will happen is there's a finite number of weights, right? Like you saw, the biggest one we drew for the spiral was 24 weights, right? 24 numbers.
Yeah.
And so it can, initially I trained it on one kind of spiral. I gave it another spiral. It might be learning to adjust those weights on the new spiral data, and it might forget. Forget meaning it is no longer adjusting the loss against in examples from that previous spiral, right? So it'll forget that one, right? So these things are called very, they can be changed, they can be influenced. All these weights are always available to learn something new. In that process, it might forget something old. Forget meaning those weights have been deleted and erased, and new weights have been added for the new task. So that's some kind of a forgetting, but it's more like not quite forgetting, but learning new things. And in that process, if some things you have to forget, then you forget.
Okay. One more related thing here in language model, say, if I am asking certain questions, is it registering that question, recording it somewhere, or no? Every time it's taking it new.
Every time it's taking it new, when you are
Okay, so it is not storing the questions.
Now, it could learn from it if you gave it.
No, I'm not talking about learning from it. For example, if for example, I'm trying to learn certain things, I will keep a register of all the questions that have been asked. For example,
Yes.
in law exam, entrance exam, CLAT, all the questions that had been asked before.
Yes.
10 years, whatever it is.
That is your training data. If you kept it and you go back to it and you go through it and memorize or understand some.
Training data remains, or
Yes.
once. Okay.
The training data can remain. Now, this is back to the forgetting. Do you want new training data? Maybe laws have changed, since 30 years ago.
Okay.
There's a new training data. The answer used to be blue. Now it is orange, in our classification. So you want to learn on more recent data, maybe more than. But this is like, your training data. Now, when you're applying it, it is just purely applying. It doesn't remember. It can be made to remember, but you're only giving it the X and the X's, and you generate some Y. And
I think Shivangi has another question.
Sir, as Sukhendu sir just said that by non-users, it will still remain. It may not erase completely, it will still remain. So, for an example, suppose I teach a kid, you should not judge a person based on this and that. That kid learns it. And then later on, something that he was biased towards happens. And he's like, oh, I should not have learned that. See, this happens. That's why I believed so and so. And the earlier learning will resurface. Would that happen with AI as well? Because it's not, it's only forgetting. The bias is not being erased, it's somewhere there.
I don't know. And if someone says they know, they're lying. Okay. uh, when you are dealing with, a handful of weights, we can figure out, we can look into it and say, okay, what changed? Did it remember that if I gave it that input, what is it going to do? And now, and what did it do before? Okay, these weights have changed, therefore it doesn't. When I have a trillion weights, I cannot do that. No one can do that. And so how much of the prior learning it has remained? Will it ever resurface? These are the kind of scary questions. If you ask anybody who built these systems, who are selling these systems, you have removed all these hate, profanity, speech filters against bias. Will I ever see something biased? They cannot say no. They can say we have done our best and whatever. They cannot say no because they don't know what is remained. Where is that memory, being stored? It's just like our human, not just like our human brain. It's not in one place that I can go and just zap that neuron and you'll forget something. It is distributed in some manner. It is generalized in some manner, and which would help in its recall in applying it, because you cannot memorize some of these things. You have to apply, learn a general principle. So then, but how is it stored? Will it ever resurface? Yeah, it is like as complex as a human brain would be in those cases.
Thank you
Human
so
brain,
much.
remember, human brain, 100 billion neurons, that's it. And seems to survive on some sandwiches, right? The power it needs is like a bowl of rice, dal, and it's happy. These machines, they need rooms full of, machines, very hot. They need gigawatts of energy, but they kind of try to do same as a human brain. So, and human brain fits on our top body and we can walk with it. And these things, are in the cloud. So
About
it is,
it's all of the order of trillions, right? That's what you mentioned.
well, the latest GPT-4 model, the OpenAI, the company, is not telling us how many neurons it has. They have indicated, people have, you can guess that it's in the order of trillions. Other models are are smaller.
Okay.
The earlier one was 700 billion. We barely can fit a 13 billion model in our computer, and we work for one of the bigger companies in the world. So the resources, the GPU resources, so a lot of these things, math, you can see these are matrix multiplications and something called the graphical processing unit, not a CPU like you have in a computer, but a GPU can do this real fast in parallel, all the matrix multiplications. Essentially, you can see these are all matrix multiplications. So it can do these things real fast, instantaneously, but they're very expensive. And now there's a global shortage of these GPUs because everybody wants to have them.
Diptiman.
Sorry, go ahead. Okay, let me just show you. That's a good question. So there are a lot of parameters that are hidden, So, yeah. So share a screen, share this screen. So remember, this is the last, we left our playground, when we were, you can see my screen now, I hope.
Yes.
So you see on the top, we didn't go over these, and thankfully none of you asked anything about it because I was not going to answer them. Some of them, there's activation, there's a learning rate, regularization, we didn't even use this, L1, L2, regularization rate. These are all what are called hyperparameters. These are parameters needed as part of the algorithm to work, the machine learning algorithm. right? These can remain the same from one model to the next model. These are just, high level characteristics. The other parameters is this weight. This weight is a parameter. This weight is another parameter. And all these weights together combine. How many weights are here? If you can do the math fast. This is like 8 times 2 plus 8 times 8 plus 8 times 8 plus 8 times 1. That many weights, right? So these are called parameters in some cases, but these are also called sometimes all that set of parameters, those weights are called. All those sets of weights are also called parameters or the model. Is that what you were asking about? Or? So it's a combination of hyperparameters and parameters. Parameters are nothing but the weights of the model, if they're using the language properly, like as we would use in a neural network context.
All right.
Okay, I hope this was useful. I know we covered a lot of things, and some of them maybe, again, you have to dig into your brain in the past to pull out, matrices and nonlinear functions and other things. But, full faith in the human brain for now.
This playground, is that open access? Anybody can
Yes. I think, yeah, it is, where is it? Sorry.
I think Diptiman might be interested, at least.
Yeah, it is open access. It is, come on.
Yeah, if it is open access, I think we can find that.
Yeah. The problem when you have all these slides, you can't find the right one.
Yeah, it was something playground/TensorFlow, or that was the URL, I guess.
This one and share this one. So now you should be seeing that's the playground TensorFlow. Don't search, if you just search for TensorFlow, there's a lot of other things, but TensorFlow playground will take you here. And this, as you can see, is a screenshot from there. It doesn't have some of the other ones I was doing, but it does have the spiral, it has a circle, it doesn't have that, my fake student data. But it has the other things that so you can play around with it. It's unfortunately the data here is limited to only these 4. I wish they had a way for you to upload.
Oh, there is some data already there.
Yeah, this is just playing with these 4 kinds of data. You see, one is the circle one.
Okay, but if somebody wants to do, can let's say import some data from Kaggle or whatever.
Unfortunately, this playground is mainly to mention what's going on. You play with data. This is the trade-off, right? Normally, there is no good data that has only two values. As soon as you have 3, now how am I going to show that 3? You have to, see it from perspective of 2 dimensions. So then you just rely. That's where you rely only on those losses. All you have is this number, the loss number. And so I got 5%, 50% loss. Oh, the bad model. I got 1% loss, good model. What it you can't visualize. But before you do that, it's good to play with it just to get an understanding of it.
Well,
that's why I thought this would be useful to show.
No, this, at least I think all of us have gotten some realistic idea of what it is. Not it's no longer just magic. One thing I would like to point out about that bias, what you mentioned, that some information, if it is with which humans should be blind, perhaps that is actually helpful for the machine. With the minority, that's something to me that's a very valuable insight that
we often ignore. We often pretend that the machine is just like us, so we should not give it all this things we are biased by. But then the reverse is also true, because the large language models, we want to give it, if you give it all our biases, it's going to be just as biased. because it's learning to predict simply the next word. This is not a simplification. This is the fact that even the GPT-4, all it is doing when it's training is learning simply to predict the next word a human has written. And then the next word after that, and so on. So any bias there will be reflected. The other case where we want to guard the system, oh, don't be as biased as us, don't tell it, be blind to certain, it can backfire.
These things are fairly, energy intensive, right?
Yes, it is a problem with the pollution. These things are very energy intensive because of these computers and their GPUs. It needs lots and lots of power. So far, we have not figured out how to fit it into, like the form factor of our brain, and low power as our brain.
No, it is order of magnitude different from our brain.
On the size, maybe you can say, with 100 billion parameter, I can do quite well. We have been playing around with 70 billion models, and they are very good. They're also quite good. We cannot play a lot with the GPT-4 for corporate, privacy reasons. But we can play with the 70 billion, which is kind of like, 100 billion. They're quite good, but they consume, I wish I knew the number, how much energy it consumes. It will be, creating a lot of carbon into the atmosphere. And that is the biggest problem, how do we fit these into a size, into a, whatever, 6 centimeter by 6 centimeter by 6 centimeter cube that can fit in our brain, and you can abuse it with alcohol and it still works mostly. You can kill neurons, it still works. That is the next frontier, perhaps. How do you make it low power?
Okay. All right. I think on behalf of everybody, I would like to thank you, Dr. Bagchi. And
You're welcome.
There were quite a few good questions from the students and with the participants rather, and it's a reasonable amount of interest, and they have stretched themselves and tried to understand. And even now there is one hand up.
Yeah, please go ahead.
Krishnashish, yes.
If one wants to learn about the building of this model, like how to build a model and how to learn from the scratch, like could you suggest?
The way you build a model from scratch, as one of the links I sent to you is about that. In the reading list, there's one about how to build these models. How to, if not, I will
share those. He has mailed me that list. I will share. I will forward it
so
to
there
all
is basically, like I said, how to play. You have this playground, but it is very limited, only 2 variables at a time. I did not even show you the x squared and the y. Okay, anyway, but doesn't matter. 2 variables to play with. In a real, you can get training data for many well-known problems, and there are in Python, which is a programming language, not the snake. There is it's simple to build models to learn from that. But then you go from understanding the models, to programming it. And I didn't want to get into that here, but there are plenty of tutorials that will give you like the introduction. I think I have a link to that, but you can find others. That most of this work is done in programming in Python, essentially.
Okay.
All right. Sorry if we took half an hour extra, but luckily.
No, I think it was not a problem at our end at all. We enjoyed it, and your day is going to start. Ours is going to end.
All
so
right.
we appreciate. Thank you very much. Thank you very much.
Enjoy the cricket game tomorrow, and hopefully we won't be disappointed.
Maybe you can build a machine to predict the outcome.
That is
Your Watson. I think many gamblers, they use it, isn't it?
Yeah, there are prediction systems.
Yeah,
Even as the game is going on,
yeah,
it's trying to give you predictions. But
depending on. But the predicted score, that is a very silly system that they use. I mean, they just multiply it by the current run rate. And
they can
that's a
do,
pity.
this is
I
where
don't know why they use such a rudimentary system to predict the score.
with all the data that you have, imagine how much training data there is for all the scores from in the past
Yeah, but
against every team, against
yes,
every
but they
player.
give a very linear prediction for the
That's good
score.
enough. There is no money to be made. Maybe there is money to be made in gambling areas, but self-respecting company will not try to
Right,
create
I
such a
guess so.
maybe there is already. Who knows? If everyone could use it, then there's no value in that
There's
prediction.
no value.
If all of us,
Right,
it's like
right.
the weather forecast. Everyone
Mhm.
gets it, so there's no value. If only few people get it, then they can bet better, and maybe they're doing it already. Anyway, sorry.
Okay, all right. Thanks a lot. Now,
Okay,
okay,
bye.
have a goodbye.
Thank you, sir.
Thank you so much, sir.
All right. I hope it was useful as well, and appreciate all whatever creating the links and coordination, Akash and Vidushi, and those of you who have asked, listened intently, and asked certain questions. Okay, thank you. I'm logging out.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.